there's no omega, there's none of that, there's no, yeah. It's just representative. Yep. Okay. And it's a useful representation. Okay. Yeah. You can use either one, and if you ever use degrees in here, there'll be a little degree symbol. But you can think of degree as just meaning, if I write 3 and then I put degrees, you can just think of this as equals 3 times pi over 180, right? So, yeah. So I will always say radians. And if I don't put a degree, you can assume that it is radians, unless I have made an error. Unlikely, right? So, okay. So anyway, so in shorthand, yes. Okay. So just to give you everything on the slide, if you add a cosine omega plus phi, the phasor version is just a angle phi. We have a phasor, say alpha angle phi. Then the function that the phasor represents is alpha cosine omega t plus phi. So if all you knew was that, right, you wouldn't know which function is being represented, so you have to kind of also know what omega is, okay? So hand wavy a little, but yeah, hopefully the definition makes sense. Okay. So they're useful, right? There's a reason that this representation is useful, and it's that sources that look like a e to the t j omega plus theta result in lots of a equal to the t j omega plus theta terms in our algebra when you go through and do it. And you have to go through and do all this like dividing out and stuff, right? And as I mentioned, right, when you apply a sinusoidal source to a circuit, the amplitude and phase can change, right? So if you have a RC circuit, you put in an AC source, the amplitude of the voltage across the capacitor could be different and the phase could be different, but the frequency won't change. If we had circuits where the frequency could change, then we need some kind of like really complex numbers to represent it, right? That would have like 3 components and so forth. Yeah, which inspired me and a friend a long time ago trying to figure out in a really boring class whether or not like if there was something we could take the square root of and like get like a new thing that was like different. So it turns out there's not. And that complex numbers constitute, I guess, a complete field or something to that degree. But I'm not really a complex number theorist type of guy. But yeah, so there are no really complex numbers, so you can't have ultra phasors for nonlinear circuits. Sorry. So what we're going to do is we're going to place our sources with a complex number anytime. And we're just so basically, if you go through and do it the way I described in the arbitrary procedure that we didn't really work through, if you did that, instead of doing it the way I said before and replacing it with a complex exponential, now we're just going to replace our cosine with this complex number. And we're just going to keep in mind throughout that that number just represents some function. OK, so let's make this more concrete. But not yet. First, let's talk about one more Ohm's law. Then we'll do a problem. OK, so we know those 2 things, right? That first thing is the kind of a doozy that we haven't proven that says for a complex exponential source, the voltage across it is equal to the current across it in time times the impedance, where impedance is defined as ZC equals 1 over j omega c, ZL equals j omega L, so forth. And we also know that the real part of those 2 things should be equal. So this is kind of bridging the gap between phasors and this other technique. Again, this is sort of a technical point, and you can learn this without having any idea why it works. So if you're confused, you can zone out for another like 50 seconds. But the basic picture here is that phasors are, anytime we talk about a phasor, they're complex numbers. Say I call them v hat and I hat. Each of these numbers just represent some cosine functions v of t and I of t. Cosine functions are just the real parts of complex exponentials. So if you want to move from that earlier thing we were saying about how complex exponentials are related by impedances, then we can just basically rewrite our Ohm's law of impedances in terms of phasors and say that these 2 phasors will be related by z. OK, so now we really got to make it concrete because we are just in crazy theory territory without a good anchor. OK, so just to give you a picture, this is the algorithm we're about to follow. And if you did the reading assignment today, you already have done one. But basically, what we'll do is replace everything with an impedance. And so at that point, we're just going to start treating all of our inductors, capacitors, and resistors as complex resistors. We're then going to replace all of our sources with their phasor representation. So for example, right, we were just saying it's just a number which is kind of bookkeeping a function. Next thing we'll do is we'll go through and solve using Ohm's law of impedances, which just says any phasor complex number is related to another by v hat equals I hat z. And we'll go through and do normal node voltage stuff. The only thing is we're going to have complex resistances. So there's going to be complex numbers popping up. And we'll end up with some set of voltage phasors. And whenever we want to go back to the real world from phasor world, so say we have a node voltage v hat. If we want to know what VA of t is, it's just going to be the magnitude of VA hat times cosine omega t plus angle V hat. Okay. And what we've got then is all these original sources we had are just going to be represented by phasors. So time's gone completely. We don't have to worry about our functions. And all throughout, there's just sort of this set of numbers. So it ends up looking a lot like any of our DC analysis with resistors. Okay. So after you've done a few, you get bored one day, come back and watch this webcast in a couple days, and everything I just said, you'll be like, yes, yes, yes. Okay. So here's one, right? So this is more or less the one in the preview I sent out. So our goal in this case, say we have an RC circuit, if we want to find I of t in steady state, given the voltage we have there and these resistor values and that frequency, what we'll do first is we'll do this thing where we replace each of our components with an impedance. And so whenever I post the homework for Friday, I've also got, I just haven't posted it yet, as cheat sheet for capacitors and inductors, as well as just phasors, the algorithm, right? So those documents will exist, yeah. But yeah, so those are done. I just need to like post them. But anyway, basically, if you go through and do the first thing, which is replacing all your components with a complex resistance, it's pretty easy. You know, any resistor is just going to be its original value, and I think it's safer really to just like, I like to omit units in these. I mean, it doesn't really, I don't know what the right unit would be, but basically, you know, ZR is going to be 10,000. For capacitors, the impedance just I'm giving you, right? It's a fact. Z is 1 over j omega c. If you do that, it'll work. If you do that, right, in this case, you plug in c, which is 10 to the minus 6th, and omega, which is 10 to the 2nd. So in your denominator, what's your exponent of t of 10? Yeah, so if you have 10 to the minus 6 times 10 squared, it's 10 to the minus 4. Yeah, so then you move it over here, and you get 10 to the 4. Okay, that's how you should think about it. If you want to do this quick, think in tens, add them, flip them. And so what you get is that the capacitor impedance is minus 10,000 J. Okay, so it's like a resistor, except it has a negative imaginary value. Okay, so next thing we want to do is replace our source, right? So we're going to bookkeep for our source. We know our source is really 5 cosine omega t, but we're just going to call it 5 angle 0. What is 5 angle 0? 5 angle 0 is a complex number. What complex number is it? So 5 angle 0, right? That's just the same as 5e to the 0. Let's see, 5e. Oh wait, sorry. Yeah. 5e to the j0. Okay. So what is that in rectangular form? 5 plus what, j? Yeah. Okay. There you go. So it's a complex number which represents our original source, but in this case, the imaginary part's 0.